Hello, let's learn about empirical formula. What is the empirical formula? Well, the empirical formula of a compound is the simplest whole number ratio of atoms or ions that are present in that compound. And we have mentioned before when we did organic chemistry. Empirical formulas can be calculated from the percentage compositions or from the molecular formula. And let's have a look at some examples. Here we have the substance, here we have the molecular formula, here we have the empirical formula. Now, for anything to have a molecular formula, it needs to be a covalent molecular substance. Ionic formulas or ionic compounds don't have molecular formulas. They have ionic formulas, which don't represent a molecule per se. That's not to say that ionic compounds can't have an empirical formula, and we'll look at that I think in the next video when we do molecular formulas. So hydrogen sulfide, the molecular formula is H2S. The empirical formula, the simplest ratio, is H2S. Can't be reduced any simpler than that. However, butane, which has a formula C4H10, we recognize there's a common factor between 4 and 10, and we can halve them and produce an empirical formula of C2H5. Glucose, we recognize that 6, 12 and 6 have common multiples, and therefore we can, of 6, and therefore we can reduce the molecular formula to the empirical formula CH2O. Sodium carbonate, being ionic, doesn't have a molecular formula, does have an empirical formula, Na2CO3. However, we need to recognize, remember how we made these formulas by charge balancing? And one of the steps is to do the charge balance, then reduce it to the lowest ratio, and therefore for ionic compounds the ionic formula will always be equal to, if we've done it correctly, the empirical formula. So what are the steps to finding the empirical formula? Well, step 1 is to write down the symbols of the elements present. Step 2 is assume that the mass of the sample is 100 grams. All the percentages become grams. So we go from having percentages to grams, because percentages should all add up to 100%, and therefore it's an easy concept to change them to grams where the sample is 100 grams. We convert the masses from grams to moles, and we should be able to do that hopefully now, and we find the simplest whole ratio of atoms by dividing all numbers of moles by the smallest number of moles. Now that sounds a bit complicated. Wait till we do an example and you'll hopefully get the idea there. And it's also a good idea, once I've done the example, to perhaps rewind this and have a read through these steps and make sure that you follow what I was doing. But we'll do it a few times and you'll get to do some sample questions as well. Now step 5 is an option one. If necessary, multiply by a factor to convert all the numbers to whole numbers. And I'll talk about that shortly. So let's do an example. We have a compound of sulfur which contains 2.4% hydrogen, 39% sulfur and 58.6% oxygen. What is the empirical formula for that compound? Step 1, hydrogen, sulfur, oxygen. Step 2 is to convert these percentages into masses of grams. So 2.4 grams, 39 grams, 58.6 grams. Now we need to convert them to moles. How do we convert a mass to moles? Well, we divide by the molar mass of the element. Hydrogen is 1, sulfur is 32, oxygen 16. That gives us the numbers 2.4, 1.2 and 3.7. Step 4 is the step that's a bit wordy, and what we are actually doing is we take the smallest number here, which is 1.2, and we divide each of the numbers by the smallest number. So this becomes 1.2 divided by 1.2, which gives us 1. 2.4 divided by 1.2 is 2. 3.7 divided by 1.2 is 3.1. So that tells us, now this bit here, we skip step 5. Now because this is 3.1, that's near enough to 3. And therefore we can just say that the ratio of hydrogen, sulfur and oxygen is 2 is to 1 is to 3. Sometimes we might write it as 2 is to 1 is to 3. Now, if we'd done this calculation here and we'd got an answer of 3.5, for example, that 5 would tell us that we need to multiply everything by 2 so to make this 7. So the ratio that we would got, hypothetically, would therefore be everything multiplied by 2, so 2 becomes 4 is to 2 is to 7, because we want to get rid of this 3.5, because you can't have half an oxygen in the formula. That's the whole point of the exercise. You've got to have whole numbers because we can only have whole atoms. Now, you may encounter some questions, let's go back to green, where you might be given 3.33 might occur, and that's telling you you need to use a factor, a multiplying factor of 3, because that's a third. The other one that you might encounter is you might encounter, just hypothetically, something that has a decimal place to 5 or very close to it, and that's telling us that the multiplying factor there is a 4, because this is a quarter. You can't have a quarter of an atom. How do you get rid of a quarter? Multiply it by 4. 4 quarters gives you a whole atom. So the multiplying factor there is 4. Now, most commonly we don't have to do step 5. We can stop at step 4 like this, okay, with a little bit of rounding, recognizing there's a little bit of sloppiness in our numbers and our rounding, and so we don't get a whole number. But be on the lookout for clues that suggest that there might be a multiplier. Okay. Now, if we were getting these numbers, usually the questions are constructed in a way to either give you 3.5 or 2.5. 0.33 is pretty rare in a question because we construct it not to confuse you. You might not believe us, but we do. Okay, and I think in the next video we'll actually do one which has step 5, so I'll be talking about that again. But for most of our cases we stop at step 4. So that gives us the formula H2SO3, which is sulfuric acid, of course. And the empirical formula can also be calculated from experiments where we're actually given the masses, so we can work out the masses, in which case we sort of step the transition across from percentages to masses because we have masses, as long as those masses add up to 100. Now have a go at these two questions here on aspirin and hydroquinone or something, and let's do another example. Now this is a variation, so it's a little bit different. In this case we want the empirical formula for a hydrated ionic compound. Remember those? These are the ionic compounds that in their lattices water molecules go in, and so when we weigh them we have to also weigh in the water molecules, and there is a strict number of water molecules that can fit into the lattice or each unit of the lattice. And so something like washing soda crystals, which you don't see that often, but if you look in your laundry you might have some. Basically they're used to wash clothes. It's sodium bicarbonate, Na2CO3, and it's manufactured by evaporating it from water in a chemical process. And so when you get the crystals of sodium bicarbonate, they have a lot of water in them, and it's a hydrated ionic compound. So if we took some of this and weighed out 5 grams of it, we're weighing out not just sodium bicarbonate, but we're also weighing out the water. So what we can do is we can put it in what's called a desiccator. Now a desiccator is either something that's got something else that sucks water in it, some chemicals, or most commonly it's just a moderate oven. So we cook it up a little bit and the water molecules get too much energy and get expelled from the lattice. And that's what they did here. They put it in a desiccator and they reweighed it once it had cooled down again in a dry environment, so the water doesn't get sucked back in, because there's a lot of water in air. so we have to keep it out of the moist air. And they re-weighed it, and it only weighed 1.85 grams. So there's a lot of water had been cast off. Let's calculate the empirical formula from that. So the first step is to work out how much water is in that 5 grams, and it's going to be 3.15 grams. Next step is to work out the ratio of the sodium bicarbonate to water. And we've got the ratio of the masses, 1.85 grams to 3.15 grams. But because they're made up of different atoms, we have to make them into moles to compare them and get the ratio. And to make them into moles, to make a mass into moles, what do? We divide by the molar mass. So this is the molar mass of sodium bicarbonate, and this is the molar mass of water. And that gives us a ratio of 0.0175 is to 0.175, and we might recognise offhand that that is the ratio of 1 is to 10. Now if we couldn't recognise that straight off, what you would do is you would divide the larger number by the smaller number, and that would give you the multiplier here. And that tells us that for every 1 sodium bicarbonate we need 10 waters. And that means we can write the chemical formula as Na2CO3 dot 10 H2Os. And that's the formula for hydrated sodium bicarbonate. So a little bit different, but again, working in moles and working in ratios. Have a go at this question. Gives you practice at doing this type of question. And in the next video, you'll be learning all about how to calculate molecular formula. See you later.